When I think about someone handling power transmission cables that operate at 1 kilovolt and may carry peak short-circuit currents approaching 2,000 amps, I imagine licensed electricians or utility line workers using specialized safety equipment. However, with the rapid adoption of EV cars, these types of powers are being handled by distracted people on their cell phones and my elderly parents. Today we will learn about advances in electronics that are helping to keep us all safe in automotive and industrial applications. Welcome to Tech Chat, sponsored by our friends at Mouser Electronics. On Tech Chat, we meet with engineering experts to learn about the latest technical innovations that are shaping and reshaping our world. Today, I'm happy to welcome Jeffery Katz, Senior Product Manager, and Bakir Abdus-Sabur, Senior Product Engineer at Panasonic Industry. Welcome to Tech Chat, gentlemen. So what are we going to be talking about today?
So today we're going to be talking about Panasonic relay technology and how it relates to EV chargers, as well as automotive battery management systems.
Well, it's a hot topic, so I'm really excited to get started. So let's jump right in.
Sounds great. So first, I'd like to talk a little bit about the EV charging system and the different modes there are as well, because the solution will depend on the type of electric vehicle charging station that it's being designed into. So generally, the way EV chargers are categorized in are, they call it mode 1, which is generally a slow AC charging, such as maybe a wall outlet in your garage. And these types of charging will pretty much take your car overnight to get a full charge out of. Generally, most of the innovation and new technology coming out today will fall into the other type of modes, mode 2, 3, and 4. So modes 2 and 3 would be considered your faster AC charging. Mode 2 is specifically an in-cable type of charger where you'll actually see the relay in the cable. And what's unique about this application is that cable can be dropped. So you need a relay in there that's very robust against shock and vibration. And then mode 3, which is probably the most common fast AC charging station, is a standalone charger where the relay is mounted in the charger itself. And that's going to be either single phase or 3-phase system, depending on where it's installed. And there's different solutions depending on the type of charger there. And then the final one is called mode 4, which is your DC fast charge. And for this one, you're going to be able to get a full charge in a matter of minutes, which is much more efficient for those charging their car from empty to full. However, the solution there will require a combination of both AC and DC contactors. So this slide here shows a little bit about navigating different standardization for electric vehicle charging. And there's quite a wide web of charging standards between IEC and UL standards. Generally, AC charging will fall under 2 different branches, whether it's IEC 61851, which is for the overall system. And then within that, there's different standards for mode 2 and 3. Also for UL in North America, generally all the standardization falls under UL 2231. And so a lot of what these standards are going to have an effect in terms of your relay performance will be dealing with things such as short circuit current ratings, as well as the ability to detect if your contacts have welded run.
Jeffrey, it seems that these systems have the potential to exposing people to currents that they're not going to run into typically in their home.
That's correct. So most of these chargers are not going to be designed for the home. They're likely to be designed in public places, whether it's commercial buildings or storefronts or hospitals or even on your highway. So you're going to be dealing with much higher currents and much higher voltages than you would normally see in a residential home.
But you're still having untrained professionals that are going to be using them.
That's correct. So safety is very critical in this type of application. And so is the ability to monitor and make sure that the insulation is functioning properly as well. So I mentioned before about how IEC and UL standards do have direct impact on relay design. Generally, the IEC 61851 requirement will have certain requirements for the relay, such as needing double or reinforced insulation, a minimum cycle load operation of 50,000 operations, and the ability to handle certain inrush currents as well. It does deviate a little bit between the different modes. So for example, mode 3, a typical 3-phase system, will require also a minimum contact gap of 3 millimeters and also have 4,500 amp short circuit current capability as well. And it also has the requirement for mechanical coupling as well, which is the ability to be able to monitor the position of the contact. That's going to be really critical to know if there's welding involved and if the relay needs to be replaced. In mode 2, which is your in-circuit cable relay, it does have a contact gap requirement. It's not quite as large. It's only 1.5 millimeters. And then there is a short circuit capacity as well, which is 6,000 amp square per second. In the UL2231 application, this is again mode 3 for single phase systems. This is generally a North American requirement, so we're looking at UL rather than IEC in this case. It does have some short circuit capacity requirement, usually 5,000 amp, and it does typically require auxiliary contacts. However, sometimes it can be done externally and sometimes it can be done in the relay. So it's really a customer preference, although from my experience, customers do prefer to be able to have that auxiliary contact within the relay because it's a simpler design, doesn't require external components such as component necessary to measure the current or voltage, and also requires less complicated firmware. In this slide, you can see the different styles of charging as well as the Panasonic solution. So the AC level 1 charging, I'm not going to talk about these relays today because these relays are pretty much general use type. The amount of current in a level AC relay is not very high. And so there's a wide amount of solutions available for level 1 charging. A lot of our development is focused more on the AC level 2 type of designs. And we have several generations of products for the AC level 2. Mainly the requirements for this application has been changing over the years, in particularly the IEC and UL requirements. So in order to keep up with this requirement, we've had several generations of product. And also, I'd like to discuss a little bit of the DC fast charging solution as well. There's both an AC and a DC component to this type of charger. And as of today, we're focused more on the AC portion of it.
Now, you mentioned that you've had to create new generations to accommodate changes in the regulations. Have those new generations also been moving up in the current capacity as these chargers become faster and faster?
Correct. So the trend in AC charging and DC charging, for that matter, is increased power to help speed up the charging and reduce timing to charge. And so we have had to increase carry current capability as well as short circuit capability for these type of chargers. So before I go into the specific series of products, I'd like to talk a little bit more in general about why Panasonic relays are especially beneficial for the EV charging space. Historically, EV charging has been done using larger contact relays, and we've been able to replace these larger contactors with our relay technology. And there's several inherent advantages to moving towards a relay. For one, they tend to be smaller in size and require less power per rate. The way that we're able to reduce the size but still carry large continuous amounts of current through the terminals is through what we call wide blade terminals. So if you look at the output terminals, they have these much wider blades that are able to dissipate the heat much better. Also, traditionally, relays have not used a lot of auxiliary contacts in the designs. This is a feature that's very common in traditional contactors. However, our newest generations are starting to implement the auxiliary contact, and that's going to allow you to monitor the contact welding state. Lastly, a lot of our relays, they also use pick and hold coil operation. So essentially, once you energize the relay, you can reduce the coil holding power, and that's going to alleviate some of the power consumption that's needed to keep the relay in the energized state. And it's also going to reduce the amount of heat that's introduced to your application due to coil temperature rise. This slide here shows a little bit about how auxiliary contacts work. Essentially, what this means is you have your main load current going through the normally open contacts, and these normally open contacts are mechanically coupled to a normally closed contact. And so if you have welding that occurs on the normally open contact, your normally closed contact isn't going to be able to close again. It's going to remain in the open position. And so using this open position auxiliary contact, you can send a signal to your system to let it know that you have contact welding and that the relay needs to be replaced.
So let me make sure I understand that. So one side is carrying the current and the other side is like sending a communication signal, and because it doesn't get through because it's open, it can detect that everything is working, or if it shouldn't be that state, not working.
That's exactly correct. This slide here shows the different methods in which Panasonic relays can make use of our low coil holding voltage. So again, the advantage here is energy saving for the system, because this is an application where the relay is going to be continuously energized. And also, you're going to improve your heat dissipation because you're generating less heat from the coil. And essentially, after 100 milliseconds of the relay being turned on, you can reduce that coil holding voltage to reduce the operating power. And that can be done in a variety of ways. The first method would be to use a CR circuit. Another would be to implement the switch type method. And probably the most common way of doing this is the third example here, which is using pulse width modulation. So generally for this, we would recommend a pulse width modulation duty ratio of 50% and to use a frequency between 20 and 100 kilohertz.
So you have values here of percentages of voltage and therefore the power. What kind of a scale are we talking about that these relays are consuming during holding?
So this slide here shows the different relay solutions we have for each electric vehicle charging station. In mode 2, where the relay is inside the cable, we don't have a product in production right now. However, we do have a design and samples available for a product that will be launching next year. What's unique about this product, it does have the auxiliary contact, and it does have the mechanical shock and vibration robustness that's required for dropping of the cable. For products that we have available today, for single-phase AC charging, we have 3 different generations of products. Originally, we had the HES series. From there, we've migrated towards the HER as a second-generation product, and we'll be introducing the HEA series coming this July. Here you can see our AC charging lineup by current and by contact arrangement. So in our portfolio, we actually have AC contactors that go up to 120 amps. However, for AC charging, most of the applications don't tend to exceed 80 amp current. So we tend to recommend products that are similar to that range, such as our 100 amp HEA or our 90 amp HEPV series. When it comes to contact arrangements, we do have a variety of contact arrangements, and depending on whether it's a single-phase or a 3-phase system, we have different recommendations. But generally, we would recommend either a 1-form A or a 2-form A with auxiliary contact options. So this is the first application I'd like to present our solutions for, which is Level 2 AC charging for single phase. This requirement is generally a North American requirement. The chargers tend to have a range anywhere between as small as 40 amps to 80 amp chargers. So you're looking at about 9.6 to 19.2 kilowatts or so. And auxiliary contacts generally preferred in the type of application as well. So our original solution, the HEPV Y6 series, was a 1-form A solution. It required 2 pieces per charger, and it did not have any auxiliary contact. Since then, we've released two new products. The first one is our HER series. So for this product, it was released as a 2-form A plus an auxiliary contact option. So with this solution, you can replace the two pieces and just have a single piece solution. And the advantage to having a single piece solution is now you only have one coil generating heat. So you're going to reduce your coil temperature rise just simply by reducing from two pieces to one. Now, our latest product, which is released in July, has a lower contact resistance compared to the original HEPV series, but it maintains the same exact size and footprint. Just we added 2 additional pins so we can incorporate an auxiliary contact onto it as well. So this is our detailed spec for the original HEPV series, which is a 90 amp relay. And again, I'd like to point out this is a PCB type relay. So it's very friendly when it comes to mass production assembly. Doesn't require any wiring terminals or screw terminals that traditional contactors have. It also does incorporate a lower coil holding power. So your nominal power would be 1.92 watts. And once energized, you can reduce that to about 480 milliwatt. This solution is our HEA relay. This is our newest solution released in July. And again, as I mentioned, we increased the power of this relay, so it's actually capable of handling 100 amps continuous current. We added an auxiliary contact to it as well. And the short circuit current rating for this has been increased as well. So now it is 5,000 amp. And this is really necessary to keep up with the latest UL standards for short circuit current rating in this application. Again, it still incorporates the low coil holding power. So this one has a maximum coil holding power of 310 milliwatts. And it still has the same footprint as the HEY6, but with the additional terminals for the auxiliary.
Well, it's really impressive that you guys continue to drive up the current handling capacity of it, but then the packages themselves are getting smaller. You've mentioned temperature as being a challenge. All those things are kind of fighting against each other. So the fact that you're able to optimize all of them is pretty impressive.
So this is the inside of the construction of our HEA relay a little bit up close. So you can see the main contact are actually, it's a twin contact, which you can find on the bottom of the relay. It's basically 2 movable arms that are connected to each other. And that creates your normally open contact. But what you'll also see is that if you follow the hinge spring upwards, you'll actually see that on the top surface of the relay is the auxiliary contact, which obviously is much smaller in size because it's only connecting signal across it. However, it is mechanically linked, and that's how you get this mirror contact structure, which allows you to detect the welding of the normally open contacts.
Well, that's pretty neat to get to see inside these. It's something that I've never been exposed to on the technology side. So there's a lot of complex mechanical and electrical engineering going on inside.
This slide shows our introduction of our HER relay. Now, this relay comes in 2 different types, actually. For now, just keeping with the single phase EV charger, we recommend the 2-form A with auxiliary contact for this application. This has a continuous current load of 80 amps across the contacts. Again, this has 2 normally open contacts, so you would only require 1 relay, and it does have the optional auxiliary contact as well. The nominal operating power for this, once you reduce the coil power to about 35% of the nominal voltage, becomes 490 milliwatts. The next application I'd like to discuss is the 3-phase AC charging application. So for this one, you're now required to cut off 3 lines plus neutral, which is going to require 4 separate contacts to do it. Generally, the current for these types of chargers doesn't go as high as a single-phase charger, looking at typically the maximum somewhere around 50 amps, but could be as low as 32 amps as well per contact. So our original solution for this type of charger was our HES relay. And this was a two-form A solution with an auxiliary contact option. However, since the release of this relay, the need for faster charging and higher current and higher short circuit current requirements have increased. And so we've introduced what is called our HE-R series. Earlier, we looked at this series as a solution for single phase. However, we also released a 4-form A version with an auxiliary contact, and that's used specifically for 3-phase charging. And so this has all of the contacts in one relay. So you're reducing from 2 pieces to 1 piece. And it also has higher carry current capability, and it also has higher short circuit current rating as well. One thing I'd like to mention is just the difference in structure between the 4A1B and the 2A1B. These relays essentially are the same size. We've just increased the number of contacts for the 4A1B. So if you were to look at the data sheet, you will notice that the 4A1B does not have as much current capability as the 2A1B. However, because the 3-phase system doesn't require as much current as compared to the single-phase system, it actually works out perfect for each application.
And the 3-phase here is, while the individual currents are going to be lower, aren't you still passing as much or even more power through the relay?
Yes, in 3-phase systems, you are actually drawing more power compared to the single phase. However, you've got that spread across 4 different contacts. So you actually have less carry current per contact than you would compared to the 2-form A version for single phase.
So as a follow-on to that, I would say that you didn't have to deal with more heat generated in this small package, so making that design challenge for you guys at Panasonic even more difficult.
That's right. And also, I might also note the switching voltage for the single phase versus the 3-phase is also going to be different. And so the relay is designed to withstand the switching voltage that's necessary for 3-phase systems. So here's the HER 4A1B relay, a little bit more detail. It does have a 50 amp maximum carry current rating, and it does have a nominal coil holding power 490 milliwatts. Again, it's a PCB solution, so very friendly for mass production, and it does satisfy the short circuit current rating as dictated by IEC 3000 amp. So here's the last mechanical relay solution that I wanted to present today, which is the DC fast charge application. Now, it requires several different types of contactors. It requires a DC contactor. It requires AC contactor. And unfortunately, we don't have a solution for either of these. However, we do have a solution as a pre-charge on the AC contactor side. So generally, the AC contactors go up anywhere between 400 to 690 volts AC and about 367 amps or so. This exceeds the switching capability of our relays. However, we can use some of our relays, such as our HER or the HEA that I presented earlier, as a solution to as a pre-charge for the AC contactors. So essentially, this is protecting the AC contactor and extending the life of that contactor. Up until this point, we've been talking about our mechanical relay solutions. And I would like to switch gears a little bit and ask my colleague to talk a little bit more about our photomos solutions. This could also be used in EV charging, particularly DC fast charging, as well as a large array of automotive applications, which include battery management systems.
Thank you, Jeffrey, for the introduction. My name is Bakir Sabor, and I am our Senior Product Engineer for our photomos devices. So here at Panasonic, we have 2 types of devices. We have our mechanical relays, which are contact types, and we have our solid-state switching devices, or otherwise known as our photomos. And these are products without physical moving contacts. So some key advantages when using our photomos: very long life, small size, high contact reliability, high switching speeds, and also no sound noise. We have a wide variety of different sizing options for these particular devices. Our TSON being our smallest device, all the way up to our AQZ, which are more higher capacity type of devices. Now, for the applications that we'll be discussing today, we have a smaller portfolio, which I'll cover in a couple of slides. And it is important to note that these devices can also control both AC and DC loads. So moving on to the comparison between electromechanical relays and our photomos, just to highlight some key differences. In terms of the output configuration, mechanical relays are a lot broader in terms of its different footprints. For example, one form A, one form B, one C's. Our semiconductor products are limited at the moment, but we are looking to expand into different contact arrangements. Output current is not terrible. Approximately 10 amps is the highest we can switch for our semiconductor devices. Output voltages are high, quiet operating sound noise due to not having any internal moving components, long contact life, high contact reliability, good for switching smaller load currents, and also switching at very high switching speeds. So these are some inherent advantages when adopting the semiconductor technology over the traditional electromechanical relays. So our value proposition for our photomos devices is that we are able to boast the best solutions through our wide variety of different options and also technical consulting using our spec reviews, which I'll get into a couple of slides after I review our automotive photomos lineups. Also very flexible with custom develop. So we offer a number of different custom part numbers for a wide variety of different requests. So please do not shy away if you don't see any particular products on our current portfolio. We may be able to provide you with a custom solution tailored specifically to your needs. And we also have a very special quality control and reliability test for automotive, using different types of special materials from our assembly, having dedicated production lines, and also passing AEC stress tests. Now, as I mentioned, we have a very wide portfolio for our photomos products. Our products specifically tailored to the automotive grade are a little bit more niche and a smaller sect from our entire portfolio. So we have a wide variety of different applications in the EV or automotive market, ranging from battery monitoring systems for battery monitoring, leakage detection, within the inverter side for switching DC link discharge, and in the battery disconnect unit for any type of relay welding detection, and specifically in EV chargers, leakage detection applications. So without further ado, I'll get into some of our products and also specific applications within this market. So for DC fast charging, we recommend our photomos for insulation leakage detection. Simply how this works is if our photomos is turned on and there is leakage passing through the device, it will alert that there has been some leakage within the system. For this specific application, we recommend our HE high voltage type. This part number is our AQV258H5. This device is pretty unique as it has a removal of the fifth pin. This increases the distance between the output terminals, further increasing the isolation voltage capabilities. So this part is a 1500 volt part, load current of about 0.02 amps, and an isolation voltage of 5000 volts. Again, the typical applications for this can be used in battery monitoring systems and specifically for leakage detection within these EV or DC fast charge devices.
So that's interesting there. So this is a DIP6 package where you've removed one of the terminals specifically for improving the performance in these applications.
Yes, that is correct. For our next slide here, the first slides were kind of covering our applications in the DC fast charging applications, but there's also similar applications within the automotive or any industrial mobility type of devices. So similar to the last slide, we also recommend our photomos for leakage detection in these areas. Now you may notice if you look at the part numbers on the bottom left, they have a designation at the end C*9. This indicates that this is a custom part. So currently all of our photomos for automotive applications are custom parts. None of them are standardized just because they're tailored specifically to each automotive application. So again, we recommend our photomask for leakage detection. If any insulation is deteriorated in the section, current passes when the relay is on, and that will signal an alarm output. So for this specific application, we offer two types of devices, one at 900 volt. If you require higher voltages, we also offer 1500 volts.
So could you elaborate a little bit on the customization? What would a customer need to bring to you to allow you to customize for their solution?
Yes. So I'll cover this a little bit in more detail in the later slides within our spec review process. But just to briefly mention, safety and reliability are very important when designing in our photomask within these automotive applications. So there's a couple of things that go into it to ensure that the customer is operating these devices properly, including derating voltage, so ensuring that you're not overdriving the device, for example. So when looking at leakage detection and where our photomask provides value in compared to different solutions in the market, such as discrete or reed relay, as you can see, our